The ocean covers more than 70% of this planet. Most of it has never been seen, not by any camera, crewed vehicle, or scientific instrument. And nowhere is this gap more stark than the Mariana Trench, the deepest place on Earth, which humanity has visited fewer than 25 times in all of recorded history. Tonight, we are going to explore why, the engineering barriers that make it so difficult to reach, how those barriers compare to what we have achieved in space, and the biological unknowns that wait in the sediment and the rock beneath the trench floor, in a darkness we may never truly penetrate. Before we go any further, take a moment to subscribe to this channel. It helps us a lot. Also, we would love to know where in the world you are listening from tonight, whether you are in a city or the countryside, on a different continent, or just around the corner. Drop your location in the comments. It is one of the things we genuinely look forward to reading. Now let's understand the Mariana Trench. To understand why the Mariana Trench is so difficult to explore, you first need to understand pressure. Not in a general sense, but in the precise physical sense that governs everything that happens in the deep ocean. Pressure is force distributed over area. We measure it in units called pascals, or more conveniently, in units called atmospheres, where 1 atmosphere equals the pressure of the air column above us at sea level. Approximately 133.25 pascals, or about 14.7 pounds per square inch. Our bodies are calibrated for 1 atmosphere. The pressure inside our tissues, our cells, our blood vessels, matches the pressure outside. We do not feel atmospheric pressure the way we feel wind or heat, because our bodies are in equilibrium with it. Remove that pressure, as in the vacuum of space, and the equilibrium fails. Increase it dramatically, as at great depth, and the equilibrium fails in the other direction. In water, pressure increases with depth in a straightforward way. Every 10 meters of water, or approximately 33 feet, adds 1 additional atmosphere of pressure. The physics behind this is simple. Water is dense, about 800 times denser than air, and its weight presses down on everything beneath it. At 100 meters depth, a diver experiences 11 atmospheres of pressure, 10 from the water above and 1 from the atmosphere at the surface. At 1,000 meters, roughly 101 atmospheres. At 5,000 meters, about 501 atmospheres. At the bottom of the Challenger Deep, approximately 10,935 meters down, the pressure reaches around 1,086 atmospheres. In absolute terms, that is roughly 15,750 pounds per square inch, or about 1,103 kilograms per square centimeter. To make that tangible, imagine the weight of a small family car, roughly 1,000 to 1,200 kilograms. Now imagine that weight being applied to a square no larger than your thumbnail. That is roughly the pressure pressing against every single point on the surface of an object at the bottom of the Challenger Deep. Not on the whole object, on every square centimeter of it, all at once. This is the basic physical reality that every engineer working on deep-sea vehicles must contend with. Everything else follows from it. The first and most fundamental barrier is the question of what you can build things from. A vehicle that descends to the Challenger Deep must carry its own breathable atmosphere for its occupants, or house sensitive electronics. In a sealed space that is surrounded by over 1,000 atmospheres of crushing pressure, the walls of that space must not fail. They must not buckle, crack, leak, or deform in any way that would allow the ocean to enter. The most intuitive solution is thick steel. Steel is strong in compression, meaning it resists being crushed, and it is relatively inexpensive and easy to work with. But steel is dense. Its density is approximately 7.8 grams per cubic centimeter, about 8 times denser than water. A steel pressure sphere thick enough to survive the Challenger deep would weigh so much that it could barely be made to float at all, even with significant additional buoyancy material attached to it. The engineering term for this problem is the pressure vessel mass fraction. The heavier your pressure vessel, the more buoyancy material you need to make the vehicle float. More buoyancy material means more volume, which means more surface area, which means more structural material needed to contain it. Each additional kilogram of pressure vessel material adds more than 1 kilogram to the total vehicle mass once these cascading requirements are accounted for. Titanium offers a better ratio of strength to weight. Its density is about 4.5 grams per cubic centimeter, roughly 60% of steel's density, while its strength and compression is comparable. Titanium is also resistant to corrosion in seawater, which matters because the deep ocean is a chemically aggressive environment that will attack many materials over time. The Deep-Sea Challenger, the submersible that James Cameron piloted to the Challenger Deep in 2012, used a pressure sphere made from steel but incorporated syntactic foam extensively in its structure. Syntactic foam is a material made from millions of tiny hollow glass spheres suspended in epoxy resin. Each sphere is only a fraction of a millimeter in diameter. Together, they create a material that is less dense than water, providing buoyancy while being strong enough to survive deep-sea pressures. But syntactic foam is not perfect. Under sustained pressure, the microscopic glass spheres can crack and collapse over repeated dives. The material that works on the first descent may compress slightly and lose buoyancy on the 10th. Engineers must account for this gradual degradation and build in safety margins that add weight and cost. Ceramics represent another avenue. Certain ceramic materials, particularly aluminum oxide and silicon carbide composites, are extremely resistant to compressive forces. They are also brittle, meaning they can fail suddenly and catastrophically, rather than deforming gradually. A ceramic pressure vessel that develops a hairline crack under pressure does not bend. It fractures. Glass, surprisingly, is one of the better materials available. Borosilicate glass, the same material used in laboratory glassware and certain cookware, handles compressive loads well and is transparent, which allows it to be used for viewport windows in deep-sea vehicles. The viewports on most research submersibles are made from thick glass cones, wider on the outside and tapering inward, so that the pressure of the water actually helps seat the viewport more firmly, rather than pushing it out. Still, no material is perfect. Every choice involves a trade-off between strength, weight, cost, workability, and resistance to the specific combination of pressure, temperature, and chemical environment found in the deep ocean. And the deeper you go, the narrower those trade-offs become. A vehicle that simply sits still under pressure is difficult enough to engineer. A vehicle that must move and act is far more challenging. Deep-sea research vehicles are not passive. They need to propel themselves, rotate cameras, extend robotic arms, open and close sample containers, operate lights, manage their own ballast, and communicate with the surface. Every one of these functions requires mechanisms that move, and every moving mechanism is a potential failure point under extreme pressure. Consider the problem of a shaft seal, one of the simplest mechanical components in a deep-sea vehicle. A shaft seal allows a rotating shaft connected to a propeller motor, for example, to pass through the hull of a vehicle while keeping water out. At sea level, this is achieved with a rubber gasket pressed against the shaft. The gasket is compressed enough to create a watertight seal without creating so much friction that it impedes rotation. Under 1,000 atmospheres of pressure, that rubber gasket is being pushed inward with enormous force. If it is too soft, the pressure deforms it, and water finds a path around it. If it is too rigid, it grips the shaft too tightly and either prevents it from rotating or generates so much heat that the seal material degrades. The solution most commonly used in deep-sea engineering is pressure compensation. The interior of the motor and shaft assembly is filled with oil, pressurized to match the surrounding ocean pressure. This eliminates the pressure differential across the seal. The seal now only needs to keep oil in and water out, not resist a pressure difference of 1,000 atmospheres. Pressure compensation works, but it introduces new requirements. The oil must not freeze at near zero temperatures. It must not react with the internal components. It must not leak. The system must be maintained correctly before every dive. And if any part of the compensation system fails during a dive, the pressure differential returns, and the seal can fail within minutes. Every joint, every cable penetration through the hull, every connection between a sensor and the vehicle's electronics represents a similar problem with a similar engineering solution and a similar set of failure modes. A deep-sea vehicle can have dozens or hundreds of such penetrations. Each one is a potential leak. In 1995, the Japanese remotely operated vehicle Kaiko became the second vehicle ever to reach the bottom of the Challenger Deep, arriving nearly 35 years after the Trieste's initial dive. Over the following years, Kaiko made multiple dives to the deepest parts of the trench and collected sediment and biological samples that formed the basis of significant scientific work. In 2003, during recovery operations in rough seas near Shikoku, a wave severed the tether connecting Kaiko's launcher vehicle to its relay vehicle. The relay vehicle was lost. Without it, the launcher could not operate. Kaiko's operational life ended not through failure at depth, but through a rope breaking at the surface. The deep ocean is not the only place where things can go wrong. The interface between the deep vehicle and its surface support is also fragile. Light is energy. It is absorbed by water efficiently and progressively. In clear ocean water, about half of all incoming sunlight is absorbed within the first meter. By 10 meters, more than 90% of the visible light from the surface has been absorbed. At 200 meters, in the clearest ocean conditions, light is reduced to a dim twilight. By 1,000 meters, it is essentially zero. The bottom of the Mariana Trench has never received a single photon of sunlight. It existed in absolute darkness for millions of years before the first human-built light reached it in 1960. When a deep-sea vehicle reaches the trench floor, it carries its own light sources, typically LED arrays or high-intensity discharge lamps. These illuminate a small area in front of and around the vehicle. But water absorbs and scatters artificial light, just as it absorbs sunlight. In the clearest deep ocean water, effective visibility is perhaps 10 to 15 meters. In water with more suspended particles, which is common near the seafloor, where sediment is disturbed by currents and the vehicle's own thrusters, visibility drops to 5 meters or less. 5 meters of visibility. In an environment covering 11 square kilometers of floor, the practical consequence of this is that a vehicle on the floor of the Challenger Deep can only directly observe a tiny fraction of its surroundings. It moves slowly, illuminating one small patch of seafloor at a time. The rest of the trench floor, everything more than a few meters from the vehicle's lights, is as invisible as if it did not exist. Sonar, which uses sound rather than light and can travel much further in water, allows vehicles to build up a picture of the seafloor topography at larger scales. Modern multi-beam sonar systems can map the seafloor at resolutions of a few meters from a vehicle hovering some distance above it. But sonar tells you the shape of the bottom, not what is on it or what lives in it. A sonar map of the Challenger Deep shows you ridges and valleys and flat sediment plains. It does not show you a sea cucumber or a bacterial mat, or a fracture in the rock beneath the sediment. For biological observation, direct visual contact is still essential. And direct visual contact means being there, with lights, close to the target, for long enough to see something. The combination of extreme depth and near-zero visibility means that a typical dive to the Challenger Deep, lasting perhaps 6 to 8 hours at the bottom, is able to visually survey an area that might be measured in hundreds of square meters. Out of 11 square kilometers of floor, the darkness of the deep ocean is not simply a sensory inconvenience. It is a fundamental limit on what we can observe, and therefore, on what we can know. Radio waves are electromagnetic radiation. They travel at the speed of light, approximately 299,792 kilometers per second, through air and through the vacuum of space. They carry vast amounts of information efficiently and reliably. Almost all modern communication technology depends on them. Seawater is a conductor of electricity. When an electromagnetic wave encounters a conductive medium, it is absorbed. The depth to which a radio wave can penetrate seawater before being reduced to essentially nothing is called the skin depth. And for typical radio frequencies, this skin depth is measured in centimeters to meters. A radio signal transmitted from a surface ship cannot reach a vehicle at 11,000 meters depth. Not even close. The signal is absorbed within a few meters of the surface. The only electromagnetic frequencies that penetrate seawater to any useful depth are extremely low-frequency signals, ELF signals, which use wavelengths of thousands of kilometers and can penetrate to roughly 200 meters. These were used during the Cold War by navies communicating with submerged submarines. But ELF signals carry almost no data. A single character of text takes seconds to transmit. They are useful only for simple command signals, not for the complex communication required to operate a research vehicle. The practical solution is acoustic communication, using sound rather than electromagnetic waves. Sound travels through water at approximately 1,500 meters per second, varying slightly depending on temperature, salinity, and pressure. Acoustic modems convert digital data into sound signals, transmit them through the water column, and reconvert them to data at the receiving end. Acoustic communication has two fundamental limitations. The first is delay. A sound wave traveling from the surface to a vehicle at 11,000 meters takes approximately 7.3 seconds. The response takes another 7.3 seconds to return. Every single command, every status update, every data packet sent between the surface and the vehicle involves a minimum round-trip delay of nearly 15 seconds. If the operator sends a command to stop the vehicle and the vehicle is heading toward a rock face, the vehicle will continue moving for 15 seconds before the stop command arrives. The second limitation is bandwidth. The amount of data that can be transmitted through an acoustic signal in a given time is tiny compared to radio. State-of-the-art acoustic modems in deep water can achieve data rates of tens of kilobits per second under ideal conditions. For comparison, a standard home internet connection operates at hundreds of megabits per second, roughly 10,000 times faster. Transmitting a single high-resolution photograph from a vehicle at the bottom of the Challenger Deep to the surface ship above takes minutes, not seconds. Streaming video in anything close to real time is not achievable. The operator of a deep-sea vehicle at the Challenger Deep is working with a control system that has a 15-second delay and a data connection equivalent to a very slow dial-up internet connection from the early 1990s. They are navigating a complex, unknown environment, almost blind, with degraded reaction times, and with limited sensory information. Autonomous vehicles which pre-program their own missions and operate without real-time human direction can sidestep the communication delay problem to some extent. But true autonomy in an unstructured environment, like the deep ocean floor, remains at the frontier of what artificial intelligence and robotics can currently achieve. A vehicle that can reliably identify interesting biological samples, approach them safely, collect them without disturbing the surrounding sediment, and then navigate back to a pickup point without any human direction, does not yet exist in a form robust enough for routine scientific work. Everything a deep-sea vehicle does consumes energy. Moving through water requires power. Lights consume power. Cameras, sensors, computers, communication systems, sample collection, all of it draws from a battery that must be carried to depth and brought back up again. The physics of energy storage are ungenerous. The amount of energy you can store in a battery is limited by the chemistry of that battery. For lithium-ion batteries, the best widely available technology, the energy density is approximately 150 to 200 watt-hours per kilogram. Every kilogram of battery you add to a vehicle gives you roughly that much energy to work with, and no more. Adding more battery to a deep-sea vehicle means adding weight. Adding weight means needing more buoyancy material to keep the vehicle neutrally buoyant. More buoyancy material means more volume, which means more surface area exposed to pressure, which means more structural material needed to contain it. Each additional kilogram of battery adds more than 1 kilogram to the total vehicle mass, once these cascading requirements are accounted for. The result is that deep-sea vehicles operate with strict energy budgets. A typical bottom time at the Challenger Deep for a well-designed vehicle is somewhere between 4 and 8 hours. During that time, the vehicle must descend to the bottom, conduct its science, and have enough power remaining to ascend safely. The science window is often shorter than it might appear. Jacques Piccard and Don Walsh, in their 1960 Trieste dive, spent only 20 minutes on the floor of the Challenger Deep before beginning their ascent. This was not entirely by choice. The cold, the limited power supply, and the fact that one of the vessel's plexiglass windows had cracked under pressure during the descent all conspired to limit their time. They had descended for nearly 5 hours and would ascend for 3.5 hours. Their window at the very bottom of the world was 20 minutes. Modern vehicles do better. James Cameron's 2012 dive in the Deep-Sea Challenger lasted approximately 3 hours at the bottom. The DSV limiting factor, operated by Caladan Oceanic during the 5 Deeps expedition in 2019, conducted multiple dives lasting 4 to 6 hours on the bottom. But even 6 hours at the bottom, after a descent of roughly 90 minutes and an ascent of a similar duration, is not much time to survey an environment of 11 square kilometers, collect meaningful biological samples, and conduct geophysical measurements. A field biologist studying a similar area of rainforest floor would spend weeks or months there. We send vehicles to the deepest place on Earth for a few hours and then pull them back up, and we call that an expedition. Near the bottom of the Mariana Trench, water temperature stabilizes between approximately 1 and 4 degrees Celsius, just above freezing. Cold is not merely uncomfortable. At these temperatures, materials behave differently. Rubber, which is used extensively in deep-sea engineering for seals, gaskets, and cables, becomes stiffer and less elastic at low temperatures. A seal that is correctly calibrated for its sealing force at 20 degrees Celsius will behave differently at 2 degrees. If the calibration does not account for this change, the seal may be too rigid at depth and fail to form a proper watertight contact. Lubricants, used in gears, bearings, and shaft seals, thicken in the cold. A grease that flows easily at room temperature may become nearly solid near freezing. Thick lubricant increases friction, which increases the torque required to turn a shaft, which requires more powerful motors, which consume more energy. Batteries perform worse in the cold. Lithium-ion cells, like most electrochemical systems, rely on the movement of ions through liquid electrolytes. Cold electrolytes are more viscous and conduct ions less efficiently. A battery pack that delivers its full rated capacity at 20 degrees may deliver 70 or 80% of that capacity at 2 degrees. This compounds the power problem. Electronics generate heat in a well-insulated pressure housing. This heat can accumulate. The engineers must design thermal management systems that allow heat to escape from the electronics without letting the cold ocean water create thermal gradients that cause other problems. At sea level, this is not particularly difficult. At 11,000 meters, the external temperature is barely above freezing, and the external pressure is 1,000 atmospheres. Every design decision that addresses one of these constraints tends to create tension with the others. The deep ocean is not just cold. It is precisely, relentlessly cold in a way that affects everything from the chemistry of materials to the physics of every mechanism on a deep-sea vehicle. Engineers must account for this across every component, every system, every interface. When they get it right, the vehicle functions. When they get it slightly wrong, they find out at depth where there is no way to fix it. GPS, the Global Positioning System, works by receiving radio signals from satellites in Earth orbit. A GPS receiver calculates its position by measuring the time delay of signals arriving from multiple satellites simultaneously. Radio signals do not penetrate seawater. GPS does not work underwater. This is not a limitation of current GPS technology that future improvements might overcome. It is a consequence of the physics of radio waves in electrically conductive media. No GPS system will ever work at depth. Deep-sea vehicles navigate using acoustic positioning. An array of acoustic transponders, either deployed on the seafloor or towed from surface ships, broadcasts signals at known positions. The vehicle receives these signals and uses the time delay between them to calculate its own position, much as a GPS receiver uses satellite signals. This system, called long baseline acoustic positioning, can achieve horizontal position accuracies of 1 to 2 meters in good conditions. That is reasonable for navigating a large flat area. But the deep ocean floor is not a large flat area. The Challenger Deep has ridges, walls, overhangs, and complex sediment structures. Navigating close to these features with meter-level accuracy requires constant position updates and careful attention to the positioning data. The speed of sound in seawater is not constant. It varies with temperature, pressure, and salinity. As a sound wave travels through the water column, it passes through layers of different temperatures and salinities, bending and scattering as it goes. This creates uncertainty in the timing measurements that acoustic positioning depends on. The deeper the water, the longer the sound travels, and the larger the accumulated error from these variations. Position accuracy at 11,000 meters is typically worse than at 3,000 meters, even with the same equipment. And depth accuracy, knowing precisely how deep the vehicle is, involves additional calculations based on pressure measurements that are also affected by temperature and salinity variations. The maps we build of the Challenger Deep are therefore not perfectly accurate. They are good, but not perfect. And that imperfection matters in an environment where the consequences of a navigational error can include losing a vehicle worth tens of millions of dollars. A 2010 survey that produced what was then the most detailed map of the Challenger Deep revealed features that had not appeared on any previous map. A 2019 survey added further detail. Each new survey finds something the previous ones missed. The shape of the deepest place on Earth is still being established. All of the engineering barriers we have described are real, but they do not exist in isolation. They are surrounded by a financial reality that shapes every decision about deep-sea exploration. Building a vehicle capable of safely reaching and operating at the Challenger Deep is expensive. The DSV limiting factor. Built by the company Triton Submarines for the 5 Deeps expedition, cost approximately $48 million to construct. That includes the pressure sphere, the propulsion system, the navigation electronics, the sampling equipment, and the safety systems. Operating the vehicle requires a ship capable of deploying and recovering it in open ocean conditions. A suitable research vessel costs several tens of thousands of dollars per day to charter and operate, accounting for crew, fuel, port fees, and maintenance. An expedition to the Challenger Deep, lasting 2 to 3 weeks, including transit time, bottom time, and contingency days, costs several million dollars in ship time alone. Add the cost of scientific personnel, equipment, sample analysis, data processing, and publication, and a single serious research expedition to the Challenger Deep can easily reach $15 to $30 million in total. For comparison, the annual budget of the National Oceanic and Atmospheric Administration's Ocean Exploration Program, one of the primary federal programs funding deep-sea exploration in the United States, has typically been in the range of $30 to $40 million per year. That is the total budget for ocean exploration across all of the world's oceans, all depths, all research questions. One serious expedition to the Challenger Deep can consume a significant fraction of a year's total funding for ocean exploration. The arithmetic is brutal. The result is that deep-sea exploration proceeds at a very slow pace. Not because the scientists are not motivated or the engineers are not skilled, but because the money to do the work is simply not there in the quantities required. There are currently fewer than a dozen vehicles in the world capable of operating at or near full ocean depth, 6,000 meters or more. Some of these are government-owned, operated by naval or oceanographic institutions. A few belong to private individuals. Only a small number are actively used for scientific research on a regular basis. For most research groups, accessing a full ocean depth vehicle requires either years of proposal writing, peer review, and competitive allocation of ship time, or collaboration with a private operator who has their own agenda and schedule. The infrastructure simply does not exist to conduct regular, systematic exploration of the deepest ocean. Each of the 8 barriers we have described is a real constraint in its own right. But they do not operate in isolation. They interact with each other in ways that make the total challenge significantly harder than the sum of its parts. Consider how pressure and temperature compound each other. A seal designed to work under 1,000 atmospheres of pressure must also work at 2 degrees Celsius. The rubber compounds that perform best in compression testing at room temperature may not perform equally well in the cold. The engineer must find a material that satisfies both constraints simultaneously, not just one at a time. Consider how the communication barrier and the power barrier interact. Acoustic communication is not only slow, it is also a significant consumer of power. Transmitting acoustic signals through several kilometers of water requires substantial electrical energy. Every watt spent on communication is a watt not available for propulsion, lighting, or scientific instruments. The engineer is constantly trading one resource against another within a budget that is already very tight. Consider how the visibility problem and the navigation problem reinforce each other. Navigation at depth depends on acoustic positioning, which gives you a position accurate to roughly 1 to 2 meters, but your camera can only see 5 to 10 meters ahead. The uncertainty in your navigation is comparable to your visual range. You may think you know where you are, but the uncertainty in your position is large enough that your camera could easily be pointed at something significant without your knowing it. These compound interactions mean that solving one barrier in isolation does not solve the problem. Building a better pressure vessel does not help if you still cannot communicate in real time. Improving acoustic bandwidth does not help if your battery life limits you to 3 hours at the bottom. Making a lighter vehicle does not help if the lighter materials are less reliable under repeated pressure cycling. Deep-sea engineering is a system optimization problem with multiple major variables that each impose hard constraints. The solution space, the set of designs that satisfy all constraints simultaneously, is narrow. Moving to solve one constraint often means moving away from the optimum for another. Progress requires finding paths through the solution space that improve the overall system without violating any single constraint too badly. This is why deep-sea vehicle design advances slowly. It is not a lack of creativity or will. It is the genuine difficulty of the optimization problem. The deep ocean has not been fully explored, not because we have not tried hard enough, but because the constraints it imposes are very hard to satisfy together. Space is not a comfortable place. In space, there is no atmosphere to breathe. Temperatures range from near absolute zero in shadow to hundreds of degrees in direct sunlight. Radiation streams through the void without the protection of a planetary magnetic field or atmospheric shield. Micrometeoroids travel at kilometers per second, and the distances involved are, by any human measure, incomprehensible. And yet, we have sent humans to the moon. We have placed a continuously inhabited station in Earth orbit and kept it running for over 20 years. We have landed rovers on Mars and driven them across its surface for years. We have sent probes to every planet in the solar system and beyond. The deep ocean, by comparison, is a few hundred kilometers away at most. It is on the same planet. It is not in a vacuum. It is not bombarded by radiation. And we have sent humans there exactly twice in crewed vehicles capable of reaching the very deepest point, in 1960 and 2012. Why? The answer is not that space is easier. It is that space and the deep ocean present fundamentally different engineering challenges, and some of the deep ocean's challenges are, in specific and important ways, harder to solve. The central physical difference between space exploration and deep-sea exploration is the direction of the pressure. Space is a near-perfect vacuum. There is essentially no external pressure acting on a spacecraft. The engineering challenge is internal, keeping the pressure in, maintaining a breathable atmosphere inside a thin metal shell surrounded by nothing. A spacecraft hull designed to keep 1 atmosphere of air inside is not under significant compressive stress from the outside. The hull is in tension, being pulled outward by the internal pressure, not compressed inward by external pressure. Structures under tension are relatively easy to design. A bicycle tire holds air at multiple atmospheres of internal pressure, with a thin rubber wall, because rubber under tension is strong and flexible. The same rubber under high external compression would collapse in an instant. The pressurized hull of the International Space Station is approximately 4.8 millimeters thick in its aluminium sections. This is thin enough to be punctured by a small meteoroid, which is a genuine safety concern. But it is structurally adequate to hold 1 atmosphere of internal pressure against the vacuum outside. A deep-sea pressure vessel, designed for the Challenger Deep, must withstand 1,086 atmospheres of external pressure. The engineering is categorically different. The wall must be thick enough to resist compressive buckling, a failure mode that differs fundamentally from the tensile failures that space structures must resist. And thick walls mean heavy structures, which brings all the weight and buoyancy problems we have already discussed. A space station and a deep-sea submersible are both pressure vessels. But one is holding pressure in against near-zero external pressure, and the other is holding pressure out against 1,000 times atmospheric pressure. These are not the same engineering problem. The second one is harder. Communication in space is constrained by distance. Radio waves travel at the speed of light, which means a signal from Earth to the Moon takes about 1.3 seconds. A signal to Mars takes between 3 and 22 minutes depending on the relative positions of the planets. These delays are significant for human spaceflight. Astronauts on the Moon during the Apollo missions had to be largely self-sufficient because real-time communication with mission control was impractical. Future crewed missions to Mars will face communication delays that make Earth-based mission control essentially irrelevant for routine operations. But for robotic missions in Earth orbit or on the Moon, communication delays are manageable. The Mars rovers operate with delays of up to 40 minutes round trip, which requires careful autonomous operation. But the rovers have successfully driven for kilometers across complex terrain. In the deep ocean, the communication problem is not distance, but medium. Sound travels through water at 1,500 meters per second, about 200,000 times slower than light. For a vehicle at 11,000 meters, the round-trip communication delay is around 15 seconds. This delay is a physical constant that cannot be reduced by technological improvement. Better acoustic modems will be faster in data transmission, but they cannot change the speed of sound. More critically, the bandwidth of acoustic communication is permanently and fundamentally limited. The physics of sound transmission through water constrains how much information can be carried per second, regardless of how sophisticated the encoding is. A state-of-the-art acoustic modem transmits data at tens of kilobits per second. A satellite internet connection transmits data at hundreds of megabits per second. Operating a deep-sea vehicle is like driving remotely with a 15-second delay, and a data connection slower than a dial-up internet connection from 3 decades ago. Operating a Mars rover involves a longer delay, but a much faster data connection, and the rover can be commanded with much higher resolution imagery and more complete situational awareness. In terms of practical operability, a vehicle on Mars is in some ways easier to work with than a vehicle at the bottom of the ocean. That is a strange truth, but it follows from the physics. One of the most important developments in both space and ocean exploration over the past 2 decades has been the growth of robotic capability. In space, robotic missions have dramatically expanded our reach beyond what crewed missions alone could achieve. The Mars rovers, the Cassini probe at Saturn, the New Horizons flyby of Pluto, these were all robotic missions that went to places no human could follow. In the deep ocean, the equivalent development is the Autonomous Underwater Vehicle, or AUV. Unlike remotely operated vehicles, which are connected to a surface ship by a tether and controlled in real time by a human operator, AUVs are free-swimming robots that navigate under their own power, guided by pre-programmed mission plans or onboard algorithms. AUVs have significant advantages for deep-sea exploration. Without a tether, they can operate in more complex terrain without the risk of the tether snagging on obstacles. They can cover larger areas than tethered vehicles in a given amount of time. They can be programmed to follow systematic survey patterns that build up comprehensive maps of the seafloor. The Nereus hybrid vehicle, developed by the Woods Hole Oceanographic Institution, demonstrated the potential of untethered deep-sea robotics when it reached the Challenger Deep in 2009. On that dive, it collected sediment samples and took video footage from the deepest accessible point. In 2014, Nereus was lost during a dive in the Mariana Trench, north of New Zealand, when it imploded under pressure at approximately 9,990 meters, or 32,776 feet. The cause was a failure in one of the pressure housings protecting its electronics. The loss of Nereus illustrated a fundamental truth about operating in the Hadal Zone. Every vehicle that goes there is operating at or near the limits of what its engineering can sustain. The margins are thin. A single small failure, One component that does not perform exactly as designed can end a mission or destroy a vehicle that took years and millions of dollars to build. Future AUVs will be more capable. Computing power has advanced. Battery technology has improved. Sensor miniaturization has made it possible to pack more scientific capability into smaller and lighter packages. But the fundamental physics of the deep ocean have not changed. The pressure is still there. The cold is still there. The darkness and the communication limits are still there. Robotics can extend our reach in the deep ocean, but they cannot bypass the physics. Every robotic vehicle that descends to the Challenger Deep faces the same set of engineering challenges as the crewed vehicles that came before it. The solutions must be found, not assumed. The space age, as we typically date it, began in 1957 with the launch of Sputnik. In the nearly 70 years since then, the investment in space exploration by governments and private companies has been extraordinary. NASA alone has spent in the range of $650 billion over its history, adjusted for inflation. This does not include the space programs of other nations, the Soviet Union's Cold War program, the European Space Agency, or the programs of China, India, Japan, and others. The Apollo program, which put humans on the moon between 1969 and 1972, cost approximately $260 billion in today's money. This figure, for a single program over roughly a decade, is larger than the total investment in ocean science from all sources over the entire history of the field. The results of this investment are extraordinary. We have sent spacecraft to every planet in the solar system. The Voyager probes, launched in 1977, have crossed the boundary of the heliosphere and entered interstellar space, still transmitting data from more than 22 billion kilometers away. The James Webb Space Telescope, launched in late 2000, has produced images of galaxies from within the first billion years of the universe's existence. We have mapped the surface of Mars at resolutions better than 30 centimeters per pixel in some areas. We know the composition of its atmosphere to parts per billion. We have found water ice at its poles, evidence of ancient liquid water in its geology, and organic molecules in its soil. Against this backdrop, consider the state of our knowledge of the Mariana Trench. The total number of dives that have reached the floor of the Challenger Deep, combining crewed and robotic expeditions, is currently around 25. Most of these have been brief. The longest anyone has spent continuously on the floor of the Challenger Deep is a few hours. Our best bathymetric maps of the Challenger Deep have a resolution of roughly 1 to 2 meters in the areas that have been surveyed most carefully, but these detailed surveys cover only portions of the trench floor. Large sections remain mapped only at much coarser resolution or not at all. We know more about the topography of the lunar surface than we do about the floor of the Challenger Deep. We know more about the distribution of craters on Mars than we know about the sediment structures of the Mariana Trench. We know more about the composition of the interstellar medium, the thin gas between star systems, than we know about the microbial communities living in the trench's sediment. This is not a comfortable fact. It is simply true. Part of the explanation is historical and political. The space race of the late 1950s and 1960s was driven by superpower competition. The United States and the Soviet Union both understood that technological leadership in space had military, political, and psychological implications. This urgency drove investment on a scale that has never been applied to ocean exploration. There was no equivalent geopolitical motivation to reach the bottom of the ocean. The Challenger Deep was first sounded in 1875 by HMS Challenger. Its extreme depth was noted and recorded, but there was no race to reach the bottom. When Pickard and Walsh made their historic dive in 1960, it attracted relatively little public attention compared to the space missions of the same era. Part of the explanation is also commercial. Space has developed an enormous commercial industry. Communication satellites, navigation satellites, Earth observation satellites. These are enormously profitable. The companies that build and operate them generate revenues in the hundreds of billions of dollars annually. This commercial activity drives investment in launch vehicles, satellite technology, and eventually in exploration beyond Earth orbit. The deep ocean has no equivalent commercial ecosystem. There are no profitable applications that require regular access to 11,000 meters depth. The infrastructure simply does not exist to conduct regular, systematic exploration of the deepest ocean. Part of the explanation may also be psychological. Space is visible. You can see the moon. You can see Mars as a bright point of light in the night sky. The deep ocean is invisible, dark, and inaccessible to ordinary experience. The wonder it generates is abstract, imagined, rather than observed. It is harder to build public excitement around something you cannot point at in the sky. None of this means the deep ocean is less important than space. The ocean regulates Earth's climate. It absorbs enormous quantities of carbon dioxide from the atmosphere. It drives weather patterns that determine where rain falls and where droughts occur. The organisms that live in it are part of ecological cycles that sustain all life on Earth. We have simply chosen, collectively and over decades, to invest more in understanding space than in understanding our own ocean. And now we live in a world where we know the far side of the moon better than we know the bottom of the sea. To put the challenge in concrete terms, consider what it would take to systematically survey the floor of the Challenger Deep at a resolution comparable to what we routinely achieve in other research environments. A marine biologist studying a coral reef typically works at depths of a few tens of meters. They can spend hours in the water. Their visibility is tens of meters in clear conditions. They can return to the same site repeatedly over years, tracking changes in the community over time. A comprehensive survey of a small reef area might take weeks or months of fieldwork. Apply the same standards to the Challenger Deep. The floor covers roughly 11 square kilometers. A vehicle with 5 meters of effective visibility must cover the entire area systematically, moving in overlapping transects at a safe speed for sample collection, accounting for the time needed to ascend and descend, and the power budget for each dive. A conservative estimate suggests that a complete biological survey of just the Challenger Deep floor would require hundreds of separate dives, at a rate of perhaps 10 to 20 dives per year. If funding and vehicle availability allowed, a complete survey would take decades. The equipment available in Decade 1 would be different from the equipment available in Decade 2. Baseline conditions might change over that time. Coordinating the data from hundreds of separate expeditions would itself be a major scientific undertaking. No such program exists. No such program has ever been proposed at a scale that would make it realistic. The Mariana Trench is famous, but it is also largely ignored as a practical object of systematic scientific study. The gap between what systematic science requires and what we have actually done at the Challenger Deep is very large. We are not behind on this program. We have not yet started it. For most of the history of ocean science, the question of whether anything lived in the deepest parts of the ocean was genuinely open. The logic of impossibility seemed compelling. No sunlight, near freezing temperatures, pressures that crush steel, scarce food, because photosynthesis, the basis of almost all food webs, cannot occur without light. The deep trenches, the argument went, must be biological deserts. Cold, dark, empty. The first concrete evidence against this view came during the original Challenger expedition, of 1872 to 1876. Using dredges and trawl nets lowered to significant depths, the expedition recovered organisms from well below the depth at which life was thought possible. Small crustaceans, worms, foraminifera. The ocean was not empty. When Pickard and Walsh reached the bottom of the Challenger Deep in 1960, they reported seeing what appeared to be flatfish through their cracked viewport. This observation has been debated, and some researchers believe what they saw may have been sea cucumbers or other organisms. But the point stood. Something was moving at the bottom of the world. Every subsequent expedition to the Challenger Deep has confirmed and expanded the picture of life in the Hadal Zone. There is life there. Quite a lot of it, relative to what the early pessimists predicted. Understanding it is another matter entirely. The Hadal Zone is defined as ocean depths below 6,000 meters, or about 19,685 feet. It encompasses the deep trenches and smaller depressions that punctuate the ocean floor in subduction zones and rifting areas around the world. The Mariana Trench is the deepest of these, but it is not unique. There are dozens of hadal environments around the Pacific, Atlantic, and Indian Oceans. The organisms that live in the Hadal Zone share a general challenge. They must maintain all the biochemical processes of life under pressures that would denature the proteins and collapse the cell membranes of surface-dwelling organisms. They do this through evolutionary adaptations at the molecular level, modifications to the structure of proteins, membranes, and enzymes that allow these molecules to function correctly at high pressure. One of the most well-studied hadal animals is the amphipod. Amphipods are crustaceans, small shrimp-like animals that are found throughout the ocean. In the Hadal Zone, they are ubiquitous. They are found in baited traps at all depths down to the floor of the Challenger Deep. They sometimes converge on a single bait source, in hundreds of individuals within hours of it being lowered. Hadal amphipods are often larger than their shallow water relatives. The species Hirondelia gigas, found in the Mariana Trench, can reach lengths of up to 34 millimeters, or about 1.3 inches. This size increase in deep-sea animals is a general pattern known as deep-sea gigantism, and its causes are not entirely understood. Lower metabolic rates, longer lifespans, reduced predation pressure, and higher dissolved oxygen concentrations at depth have all been proposed as contributing factors. Sea cucumbers, soft-bodied echinoderms related to sea urchins and starfish, are also found on the floor of the Challenger Deep. They move slowly across the sediment surface, ingesting it and processing the organic material within it. They are, in a sense, the earthworms of the deep ocean floor, cycling organic matter and nutrients through the sediment. The Mariana snailfish, Pseudoliparus swiri, discovered and formally described in 2014, holds the record as the deepest fish ever recorded. It has been observed and collected at depths of up to 8,336 meters, or 27,349 feet, in the Mariana Trench. It is a small, pale, gelatinous animal, roughly 30 centimeters long, that appears almost translucent under the lights of a deep-sea camera. Its scientific name commemorates Sub-Lieutenant Herbert Swire, a crew member on the original HMS Challenger expedition. Beyond these relatively well-studied organisms, the biological community of the Challenger Deep remains largely unknown. The sampling that has been done is patchy and limited. Species collected in one part of the trench may not be present in another. The sediment community, which includes organisms too small to be seen without microscopy, has barely been studied. The visible animals of the Challenger Deep, the amphipods and sea cucumbers and snailfish, are the conspicuous part of the community. The invisible part, the microbial community in the sediment, is arguably more important and certainly less understood. The sediment at the bottom of the Challenger Deep has been accumulating for millions of years. It is a mixture of clay minerals eroded from continents, the shells of microscopic organisms that once lived in surface waters and sank after death, and chemical precipitates from the water column. In the trench, this sediment is deeper and finer than on the surrounding abyssal plain, because the trench's geometry concentrates settling material. Within this sediment, live communities of bacteria and archaea, single-celled organisms that constitute two of the three great domains of life. These organisms are not simply surviving in the trench sediment. They are active, metabolizing, reproducing, and playing important roles in the cycling of organic, carbon, nitrogen, and other elements. A 2013 study, published in the journal Nature Geoscience, examined sediment cores from the Challenger Deep and found that the density of microbial cells in the trench sediment was significantly higher than in sediment from the surrounding abyssal plain at similar depths below the seafloor surface. The researchers attributed this to the trench's role as a trap for organic material settling from above. More food means more microbial activity. More microbial activity means more cells. The same study found evidence of active carbon processing at depths of up to 10 centimeters below the sediment surface. The microbes were not just sitting in the top layer of sediment. They were active throughout the upper sediment column, consuming organic material and releasing carbon dioxide. What this means for our understanding of the deep ocean's role in the global carbon cycle is significant. The deep ocean, including the Hadal trenches, is thought to be a net sink for organic carbon, meaning it removes carbon from circulation and stores it in long-term sediment deposits. If the Challenger Deep's microbial community is more active than previously assumed, the rate at which this carbon processing occurs may have been underestimated. The microbial community in the Challenger Deep is one of the least studied biological systems on Earth. We know it exists, we know it is active. We know it contains species not found elsewhere. Beyond that, the details remain largely obscure. The sediment at the bottom of the Challenger Deep is not just a habitat. It is a record. Each year, a thin layer of material settles onto the sediment surface, the remains of microscopic organisms from the sunlit surface waters, clay particles carried by currents, chemical compounds precipitated from the water column. Over millions of years, these layers have accumulated, one on top of another, building up a sediment column that contains a compressed archive of the history of the ocean above it. Reading this archive requires extracting sediment cores, carefully pulling long cylinders of sediment out of the seafloor, and analyzing them layer by layer. In the sediment cores recovered from the Challenger Deep, researchers have found evidence of past ocean conditions stretching back millions of years. The composition of the sediment, the species of foraminifera preserved in it, the chemical signatures of carbon and oxygen isotopes, all of these encode information about ocean temperatures, productivity, and chemistry at the time each layer was deposited. The sediment cores from the deepest ocean trenches are particularly valuable for this kind of research because the trenches are depositively environments. Material accumulates in them rather than being eroded away by currents. A sediment core from the Challenger Deep may contain a continuous record of ocean history that would be interrupted or absent in a core from a shallower location subject to current activity. This record also contains a history of the life that has inhabited the trench. Preserved in the sediment are the remains of organisms that lived and died there, some dating back millions of years. Comparing these fossil assemblages to the living community allows researchers to ask questions about how the community has changed over time and how it has survived mass extinction events that devastated life at the surface. We have only scratched the surface of this archive, The sediment cores recovered from the Challenger Deep represent a tiny fraction of the available record. The deeper history, the record of the trench under different ocean conditions over geological time, remains largely unread. Organisms adapted to live under high pressure have a technical name: piezophiles, from the Greek piezein, to press. The study of piezophilic biology is a relatively young field, having developed only in the past few decades as the technology to collect and study high-pressure organisms has improved. What makes pressure so challenging for biological systems is its effect on molecular structures. Proteins, the workhorses of biochemistry, are folded into specific three-dimensional shapes that determine their function. This folding is driven by a balance of chemical interactions within the protein molecule. High pressure disrupts this balance, causing proteins to unfold or denature into random shapes that can no longer function. Cell membranes are also affected. Membranes are made from phospholipid bilayers, two layers of fatty molecules arranged with their water-avoiding tails facing inward and their water-loving heads facing outward. At normal pressure and temperature, the membrane is fluid enough to allow proteins to move within it, but structured enough to maintain its barrier function. High pressure tends to solidify membranes, reducing their fluidity and impairing their function. Piezophilic organisms have evolved molecular solutions to these problems. Their proteins have different amino acid compositions at key positions, allowing them to fold correctly under high pressure. Their membranes contain higher proportions of polyunsaturated fatty acids, which remain more fluid under pressure than the saturated fatty acids common in surface organisms. Some of the most extreme piezophiles recovered from deep-sea sediment cannot survive at surface pressure at all. They are obligate piezophiles. Remove the pressure, and their biology fails. Bring a sample of Challenger Deep sediment to the surface, and some of its resident microbes will begin to die during the ascent, as pressure decreases through levels they cannot tolerate. This is one reason why studying hadal microbes is so difficult. The act of collecting and recovering them kills a portion of them. The survivors are a biased sample, the organisms most tolerant of depressurization, not necessarily representative of the community as a whole. Researchers have developed pressurized recovery systems, containers that maintain deep-sea pressure around sediment samples during the entire recovery process. These systems allow obligate piezophiles to remain alive and viable at the surface, where they can be cultured and studied in pressure chambers. But these systems are expensive, mechanically complex, and not yet widely available. The organisms we most want to study are the ones that die before we can study them. This is one of the central frustrations of hadal biology. Trenches are physical traps. Their geometry, a narrow depression in the seafloor, means that material falling through the water column above tends to funnel into them. Organic particles, dead organisms, chemical compounds, anything that settles toward the seafloor is more likely to end up in the trench than on the surrounding flat plain. This concentration effect is beneficial for the organisms living there. More organic material means more food, but it also means that the trench accumulates things we would rather were not there. Polychlorinated biphenyls, known as PCBs, are synthetic organic chemicals manufactured from the 1930s onward and used extensively as electrical insulators and in various industrial applications. Their persistence in the environment, resistance to biological degradation, and tendency to accumulate in fatty tissues were recognized as serious problems, and most countries banned them by the early 1980s. By that time, they had been distributed throughout the global environment. In 2017, a study published in the journal Nature, Ecology, and Evolution reported PCB concentrations in amphipods collected from the Challenger Deep that were between 15 and 50 times higher than concentrations found in crustaceans. from one of the most industrially contaminated river systems in China. The amphipods at the bottom of the deepest ocean trench contained higher concentrations of industrial chemicals than animals living in one of the most polluted surface environments in the world. Microplastics have also been found in the Challenger Deep. A 2019 study analyzed amphipods collected from the trench and found plastic fibers and fragments in every single individual examined. The plastic types identified included polyethylene terephthalate, found in plastic bottles and synthetic clothing fibers, and nylon, among others, every single one. We do not know what these contaminants are doing to the biological community of the Challenger Deep. We do not know whether PCBs bioaccumulate up the hadal food web as they do in surface ecosystems. We do not know whether microplastics affect the gut microbiome of hadal amphipods or interfere with the feeding and digestion of sediment processing organisms. We have sent our chemistry to the bottom of the ocean, and we are only beginning to ask what it has done there. The Mariana Trench is not the only deep trench in the world. There are dozens of hadal environments distributed across the Pacific, Atlantic, and Indian Oceans. Each one sits below 6,000 meters. Each one is isolated from the others by vast stretches of shallower ocean floor. For an organism adapted to live at 11,000 meters of depth, the surrounding abyssal plain at 4,000 to 5,000 meters is not simply shallower. It is potentially lethal. The pressure at 4,000 meters is about 400 atmospheres. An obligate piezophile, calibrated for 1,000 atmospheres, would experience 400 atmospheres as severe depressurization. The abyssal plain between trenches may be as effective a barrier for deep-sea organisms as mountain ranges are for some terrestrial ones. This isolation has evolutionary implications. If the populations of organisms in different trenches cannot exchange individuals, they will gradually diverge genetically. Over millions of years, populations in the Mariana Trench and populations in the Tonga Trench in the Southwest Pacific may evolve in different directions, adapting to the specific conditions of their particular environment, and eventually becoming distinct species. Studies comparing the fauna of different deep trenches have found both similarities and differences. Some species appear to be distributed across multiple trench systems, suggesting that dispersal between trenches is possible, at least for some organisms. Others appear to be restricted to a single trench, suggesting effective isolation. The mechanisms of dispersal between trenches, how organisms cross the abyssal barrier if they do at all, are not well understood. If hadal organisms are effectively isolated in their trenches, then each trench may harbor a distinct community of organisms that has been evolving independently for millions of years. The Mariana Trench would then not be representative of the hadal zone in general, but would be a unique biological environment with its own evolutionary history and its own set of adaptations. We cannot yet say confidently whether this is the case. We have sampled too few trenches too incompletely to draw firm conclusions about their biological distinctiveness. What we can say is that the question is real, and the implications are significant. If every deep trench is biologically unique, then our current ignorance is not a single gap. It is dozens of gaps, one for each of the hadal environments we have never properly studied. Here is where our understanding becomes genuinely uncertain. The floor of the Challenger Deep is the sediment surface. This is the deepest point accessible to our instruments. When we measure the depth of the Challenger Deep at approximately 10,935 meters, we are measuring the distance from the ocean surface to this sediment layer. But the sediment is not solid rock. It is soft, unconsolidated material, accumulated over millions of years. Beneath it is the oceanic crust, basaltic rock that forms the outermost layer of the Pacific Plate, and the oceanic crust is not impermeable. It is fractured, porous, and threaded with fluid-filled channels. We know that microbial life exists within oceanic crust. Scientific drilling programs have recovered core samples from oceanic crust at various locations around the ocean floor, and these samples have contained viable microbial cells at depths of several hundred meters below the seafloor surface. The organisms living in this crustal rock survive on chemical energy from water-rock reactions, extracting electrons from reduced iron and sulfur compounds in the basalt. How deep the life within oceanic crust extends is not known. Drilling programs have been limited by technical and financial constraints. Whether life extends beyond a few hundred meters below the seafloor, perhaps to the boundary between the crust and the upper mantle, is an open question. We have never drilled through the sediment of the Challenger Deep into the oceanic crust beneath it. The engineering challenges of drilling at full ocean depth are significant. The pressure at the seafloor is already 1,086 atmospheres. Drilling equipment must be lowered through nearly 11 kilometers of water and operated remotely. The scientific drilling vessels that exist for ocean floor drilling work primarily at depths of 2,000 to 5,000 meters, not at full Hadal depth. What lies beneath the sediment of the Challenger Deep is therefore inferred rather than observed. Based on what we know about oceanic crust elsewhere, we can model its composition and structure. Based on what we know about the deep biosphere in other settings, we can reason about the likelihood of microbial life in the rock beneath the trench. But we do not know. The Mariana Trench formed through subduction. The Pacific Plate, one of the largest tectonic plates on Earth, is moving westward across the Pacific Basin at a rate of approximately 5 to 10 centimeters per year. Where it meets the smaller Mariana Plate to its west, it dips beneath it and sinks into the mantle. This process, subduction, creates the trench as the downgoing plate bends and tears the ocean floor. Subduction is not a gentle process. The Pacific Plate bends sharply as it begins its descent. This bending generates enormous stress in the rock, fracturing it along fault lines that run perpendicular to the trench axis. These faults, called bending-related faults, create deep cracks in the oceanic crust, extending from near the seafloor surface down through the crust and potentially into the uppermost mantle. These fractures are not hypothetical. Seismic surveys of the Mariana subduction zone have imaged them. They are a known feature of the geology. Seawater percolates into these fractures as the plate descends, a process called serpentinization, where water reacts with the mantle rock and converts it to a mineral called serpentinite, while releasing hydrogen. This hydrogen can serve as a chemical energy source for microbial life. The fractures in the descending Pacific Plate beneath the Mariana Trench therefore create a network of fluid-filled channels that extend far below the sediment surface. They extend below what we call the floor of the trench. They extend below the oceanic crust into the upper mantle. They carry water, and where there is water in a rocky matrix with chemical energy available, there may be life. Our measurement of the depth of the Challenger Deep is a measurement of the water-sediment interface. It tells us how deep the water column is. It does not tell us how far down the physically accessible space extends below that interface. In some subduction zone settings, fractures in the descending slab have been inferred to extend many kilometers below the surface. The geometry of subduction can create void spaces, fluid-filled channels, and chemically active zones that persist deep into the slab as it descends. Whether any of this is accessible to biology is a question that has barely been asked, let alone answered. What we call the bottom of the Mariana Trench is the deepest point we can currently measure. It is not necessarily the deepest point that exists. The history of deep-sea engineering is, in many ways, a history of learning what not to do. Each vehicle built for Hadal work has taught its designers something that could not be learned any other way. The Trieste, which made the first crewed descent to the Challenger Deep in 1960, was not designed for scientific work. It was a bathyscaphe, a vessel designed purely to reach depth and return. Its sphere was thick-walled steel, its buoyancy provided by a large tank of aviation gasoline, which is less dense than water. It could not maneuver horizontally. It could not take samples. It descended. It arrived. It ascended. The science it could do was essentially limited to looking through a cracked viewport for 20 minutes. The lessons of the Trieste informed every subsequent vehicle design. Engineers understood that depth alone was not enough. A vehicle had to be capable of doing something useful once it arrived. This required propulsion, which required moving parts, which required pressure compensation. It required lighting, which required larger batteries, which required more buoyancy. It required cameras, which required transparent viewports, which required thick glass cones precision ground to tolerances of fractions of a millimeter. It required communication with the surface, which required acoustic transducers capable of transmitting and receiving through kilometers of water without distortion. Each requirement added weight. Each addition of weight required a countervailing addition of buoyancy. The design process was a constant negotiation between the desire to add capability and the hard physics of buoyancy and mass. Every vehicle that has reached the Challenger Deep represents a compromise, a set of decisions about which capabilities to include and which to sacrifice. The Deep-Sea Challenger, James Cameron's vehicle, was optimized for filming. It carried extensive camera systems and lighting at the expense of sample collection capability. The DSV limiting factor was optimized for repeatability and scientific versatility, capable of being reconfigured for different scientific missions. There is currently no vehicle that can do everything scientists would want to do at Hadal depth. A vehicle capable of carrying a complete suite of geophysical sensors, biological sampling equipment, sediment coring tools, water sampling systems, and high-resolution cameras simultaneously would be so heavy and so large that it would barely be able to descend, let alone maneuver usefully at the bottom. The vehicles we have are compromises. The vehicles we can build with current technology will continue to be compromises. The question is which compromises to make, and that question is answered differently depending on who is funding the expedition and what science they want to do. There is one more engineering challenge worth considering, and it is one that is often overlooked: the surface ship itself. A deep-sea research vehicle cannot operate without a capable surface support vessel. The ship must be large enough to carry the vehicle, its handling systems, and the scientific equipment. It must be stable enough to deploy and recover the vehicle safely in the sea conditions found at the Mariana Trench, which are not always benign. It must have the endurance to steam to the trench, conduct operations, and return, which is a journey of many days from the nearest major port. The combination of vehicle and ship is an expensive and logistically complex system. If either component fails, the entire expedition fails. In 2003, the loss of Kaiko's secondary vehicle during the storm ended the mission. There was nothing wrong with the primary vehicle itself, but without its relay component, it could not operate. The interdependence of vehicle and ship means that the weakest link in a very long chain determines the outcome of every expedition. Space exploration has benefited enormously from the dual-use nature of much of its technology. Rocket engines developed for military ballistic missiles became the launch vehicles that sent the first satellites and astronauts into orbit. Military reconnaissance satellite technology became the basis for civilian Earth observation satellites. Cold War competition between superpowers funded the development of technologies that had clear military applications, and incidentally, advanced scientific exploration as a byproduct. deep-sea exploration has had no equivalent military driver. Submarines are militarily important, but they operate in relatively shallow water by the standards of the Hadal Zone. No submarine has ever been built with the operational requirement to reach 11,000 meters. The military interest in the deep ocean is primarily acoustic, concerned with how sound travels through the deep ocean in ways that affect submarine detection, not with physical access to the Hadal Zone. The result is that deep-sea engineering has had to develop its technology from scratch, without the implicit subsidy that space engineering received from Cold War defense budgets. Every advance in deep-sea vehicle capability has had to be justified on its own scientific or commercial merits. And those merits, while real, have never been compelling enough to attract funding on the scale that the space race provided. Private investment has begun to change this equation, at least at the margins. Victor Vescovo, the American investor and explorer who commissioned the 5 Deeps expedition, spent approximately $48 million building the DSV limiting factor and conducting the expedition. The result was a vehicle that is genuinely capable of repeated operations at full ocean depth and a series of dives that produced scientific data not available from any previous expedition. But private funding of this kind is not systematic. It depends on the interests and resources of specific individuals. It cannot be planned, cannot be relied upon, and may or may not continue. The development of a genuine scientific infrastructure for Hadal research requires sustained institutional funding over decades. That funding has not yet materialized in the quantities required. The contrast with space is not simply about money. It is about the institutional machinery that money builds. NASA, ESA, JAXA, these are organizations with thousands of engineers and scientists, with in-house expertise spanning propulsion, communications, robotics, material science, and mission operations. They train people. They retain knowledge. They develop technologies over decades with consistent mission focus. There is no equivalent organization for Hadal exploration. Research on the deep ocean is distributed across dozens of universities, national laboratories, and oceanographic institutions, each working on different problems with different funding sources and different vehicle access. The knowledge base is fragmented. The institutional memory is thin. When a vehicle is lost, as Nereus was in 2014, the engineering knowledge that went into it is not automatically preserved and built upon. It must be reconstructed, at cost, by the next team that decides to attempt something similar. The discovery of life at hydrothermal vents in 1977 did more than add a new ecosystem to the biological catalog. It changed the question of where life might exist in the universe. Before 1977, the assumption was that life required sunlight. After 1977, the requirement was revised. Life requires liquid water and a source of chemical energy. These conditions are far more common in the universe than sunlight reaching a planetary surface. Astrobiologists, the scientists who study the potential for life beyond Earth, have taken the lesson of the hydrothermal vent community seriously. The moons of Jupiter and Saturn, particularly Europa and Enceladus, are now considered among the most promising targets in the search for extraterrestrial life. Europa is believed to have a liquid water ocean beneath its ice shell, kept liquid by tidal heating from Jupiter's gravity. Enceladus is actively venting water vapor and organic compounds from its south pole, evidence of a subsurface ocean in contact with a rocky seafloor. If life can exist at the bottom of the Mariana Trench, powered by chemistry rather than sunlight, then life might exist in the subsurface oceans of these moons. The organisms of the Hadal Zone are, in this sense, more than interesting biology. They are existence proofs for the possibility of life in conditions far beyond Earth's surface. The piezophilic organisms of the Challenger Deep may be among the most astrobiologically relevant organisms on Earth. Yet they remain among the least studied. The investment required to understand them thoroughly would be a fraction of the cost of a single robotic mission to Europa's surface. The returns in terms of understanding the potential for life in the cosmos might be comparable. There is a broader point here about the value of studying extreme environments. The organisms that live in the most challenging places on Earth have had to solve problems that organisms in more comfortable environments have never faced. Their solutions are often novel and sometimes useful in ways that could not have been predicted. The enzymes of thermophilic bacteria from hot springs led directly to the PCR technology that underlies modern genomics and medicine. The antifreeze proteins of Antarctic fish have been studied for applications in food preservation. The pressure-resistant proteins of piezophilic bacteria are of interest to industrial biotechnology for processes that require high-pressure conditions. We do not know what the Challenger deep sediment contains that might be useful. We have not sampled it enough to find out. The biological resources of the Hadal Zone, both in terms of scientific knowledge and potential practical applications, remain almost entirely unexplored. One final biological mystery deserves attention, and it concerns not what lives in the trench, but how it got there. The ancestors of the organisms living in the Mariana Trench were not always deep-sea creatures. The trench itself has a geological age. It formed through subduction processes that have been operating for tens of millions of years. But the trench as it exists today, at its current depth and configuration, is a relatively recent geological feature in the context of the history of life on Earth. The organisms that colonized it must have done so from shallower environments, gradually adapting over generations to increasing depth as the trench deepened. This process, the gradual colonization of an environment that was becoming progressively more extreme, raises questions about the pace of adaptation. How quickly can organisms evolve to tolerate increasing pressure? Which lineages were best pre-adapted for the transition? Did Hadal colonization happen once, from a single ancestral group, or multiple times from different surface or shallow water lineages? Are the amphipods and sea cucumbers and bacteria of the Challenger Deep descended from organisms that were already extremophiles in some other respect, perhaps cold water specialists from the Antarctic? Or are they descended from generalists that happened to be present when the trench was shallower and more accessible? These are evolutionary questions, and they require both genetic data from living organisms and paleontological data from the sediment record. We have some of the former and very little of the latter. The evolutionary history of the Hadal community remains almost completely unknown. Consider also what the deep biosphere tells us about the origin of life on Earth. The earliest life may have arisen not at the sunlit surface, but in hydrothermal systems, in the warm, chemically rich fluids circulating through the crust of the early Earth. If the organisms living in the rock beneath the ocean floor are descendants of some of the earliest life on Earth, then studying them is not just about understanding the present. It is about reading a very deep past. The sediment cores from the Challenger Deep extend back millions of years. The rock beneath those sediments is hundreds of millions of years old. The organisms living in that rock may have lineages stretching back to the earliest era of life on Earth. Their genomes may contain ancestral sequences, molecular records of ancient chemistry, that are not preserved anywhere else. We do not know because we have not looked. And that, perhaps, is the most honest summary of where we stand with the Mariana Trench. At nearly every level of inquiry, from the engineering of the vehicles we use to get there, to the communication systems that connect them to us, to the biology of the sediment and the rock beneath it, to the evolutionary history of the organisms that live there, the answer to most of our questions is the same. We do not know. because we have not looked. It would be wrong to leave the impression that nothing is changing. It is changing. Slowly, and with the constraints we have described very much in place, but changing nonetheless. Battery technology is improving. Lithium-ion cells are being gradually replaced in some applications by lithium-sulfur cells and solid-state batteries that offer better energy density. For deep-sea vehicles, even a modest improvement in energy density translates directly into longer bottom times or reduced vehicle mass. Neither breakthrough has yet arrived at a scale that transforms Hadal exploration, but the trajectory is in the right direction. Computing power and artificial intelligence are advancing in ways that may eventually make autonomous deep-sea vehicles far more capable than anything currently available. A vehicle that can genuinely navigate complex, uncharted terrain, identify biological samples worth collecting, approach them without disturbing the surrounding sediment, and execute a full scientific survey without any real-time human direction would be transformative. The building blocks for such a vehicle exist. Assembling them reliably enough to trust in the Hadal Zone is still years or decades away. Sensor miniaturization is allowing more scientific capability to be packed into smaller and lighter packages. Environmental DNA sampling, which captures fragments of DNA shed by organisms into the surrounding water, can be done with a device small enough to be carried on almost any deep-sea vehicle. A single eDNA sample from the water column above the Challenger Deep contains genetic traces of every organism that has recently moved through that water, from bacteria to fish. This technique is beginning to give researchers a broader picture of the biological community, without requiring them to physically collect every organism. These technologies, combined with the continued interest of private explorers and the slow but real growth in institutional support for deep-sea research, suggest that our knowledge of the Mariana Trench will be better in 20 years than it is today. More dives, better maps, more sediment cores, more genomic data, a clearer picture of the microbial community and its role in global biogeochemical cycles. But even with all of this progress, the most fundamental limits will remain. Pressure will still crush inadequate materials. Darkness will still limit visual observation to a small circle of illuminated seafloor. Acoustic communication will still impose its delay and its thin bandwidth. The cold will still affect every seal, every bearing, every battery in every vehicle. These are not engineering problems waiting for solutions. They are physics. The Mariana Trench will remain, for a very long time, a place we can only visit briefly, see only in fragments, and understand only partially. The question is how much we choose to invest in those fragments. How many dives? How many samples? How many sediment cores and genomic sequences and sonar surveys? Each one adds a small piece to a picture that remains, for now, mostly dark. The ocean does not give up its secrets easily. It never has. Every measurement we have taken of the deep has been bought with engineering ingenuity, institutional patience, and a fair amount of luck. Every sample we have brought back has survived a journey that many samples have not. And still, what we have is so little compared to what is there. The Challenger Deep is 11 kilometers below the surface of the Pacific Ocean. It is cold and dark and silent. Nothing in its long history has prepared it for our curiosity. It does not know we are looking. It does not know how few times we have looked. But we know. And that knowledge, if nothing else, should be enough to keep us looking. We have been to the moon. We have sent probes beyond the edge of the solar system. We have photographed galaxies so distant that the light reaching our telescopes left them before Earth existed. And the deepest place in our own ocean has received fewer human visitors than the moon. The engineering barriers are genuine. Pressure that destroys our best materials. Darkness that limits what we can observe to a few square meters at a time. Communication delays and bandwidth limits that make real-time operation almost impossible. Power supplies that give us hours, not days. Cold that affects every material and every mechanism in ways that compound each other. Navigation systems that work, but not perfectly, in an environment where imperfection matters. The comparison to space is humbling. Not because the ocean is harder than space in every respect, but because the specific ways in which it is harder have proven more resistant to the kinds of engineering solutions that drove the space program forward. Compression is harder to design against than containment. The speed of sound cannot be improved upon. Darkness at this depth has no equivalent in the void of space, where radio waves can always reach a receiver. And in the biology, we are only beginning to grasp the scale of what we do not know. Organisms adapted to pressures that would stop our biochemistry cold, living in sediment that has been accumulating since before the ice ages. A deep biosphere extending into the oceanic crust, whose lower boundary we have not found. Species we have collected, but not yet named. Genomes we have sequenced, but not yet understood. Chemical communities we have detected, but not yet characterized. And contaminants we have put there ourselves. PCBs at 50 times the concentration found in one of the most polluted rivers on Earth. Plastic fibers in every amphipod ever examined from the trench floor. We have sent our chemistry to the deepest place on Earth, without ever fully exploring it first. What we call the bottom of the Mariana Trench is a measurement. It is the distance from the ocean surface to the sediment layer at the deepest point of the Challenger Deep. It is a real number, measured carefully with good instruments to a reasonable accuracy. But beneath that sediment, the rock continues. The fractures continue. The fluid-filled channels descending into the subducting Pacific Plate continue. And whether they are empty or whether they carry life into depths we have not thought to look is a question for which we currently have no answer. Every expedition to the Challenger Deep has found something unexpected. Every sediment sample has contained organisms not previously known. Every survey has revised the map. The pattern is consistent. We look, and we find something we did not anticipate. Given that pattern, and given how little we have actually looked, what might a complete survey of the Challenger Deep reveal? We do not know. But consider this. In 2022, a bathymetric survey of the Challenger Deep, using a new generation of autonomous underwater vehicles, detected a series of small depressions in the sediment surface that had not appeared on any previous map. Their origin is uncertain. They may be caused by the escape of gas or fluid from beneath the sediment. They may be biological in origin. They may be geological. The researchers who found them noted that further investigation would be required. Further investigation has not yet been conducted. Beneath those depressions, the sediment waits. Beneath the sediment, the fractured crust descends into the subduction zone. And in those fractures, where water meets rock in the dark beneath the deepest ocean floor, something may be happening that no human instrument has yet reached. The Challenger Deep is named after HMS Challenger, the ship that first measured its depth in 1875. Its crew lowered a weighted hemp line over the side and counted the meters as it paid out. They felt the line go slack and concluded they had found the bottom. They had found the bottom of the water column. What lies below the bottom of the water column is a question that 150 years of subsequent science has barely begun to answer. The line may have touched the sediment, but we have not yet touched what lies beneath it.